Welcome to What Makes You Tick. TIQ. Think, imagine, question. Alright, anyway. You know, the scientific consensus is that the climate is shifting. We see it all around us. Frequently we experience extreme environmental conditions. And the question is, how do we respond? As an architect, I designed the built environment around us. And what interests me is how humans can manipulate the terrestrial conditions in a constructive and sensitive way. This is ultimately how the research journey begins. The quest of discovery, if you will, from understanding the fundamental physical world to exploring the lateral ingenuity and innovation for extreme environments in space. Intent is for the collated data to be shared as a resource and inform the design of the built environment from macro to micro scale. We study the natural world and speak to some of the frontier thinkers, astronomers and space engineers. First, we visit CERN, the European Organization for Nuclear Research in Geneva, Switzerland. This is a place where profound questions are being posed. What is the nature of our universe? What is it made of? The scientists probe the fundamental structure of the particles that make up everything around us. They do so using the world's largest and most complex scientific instruments. What we observe is that, like the International Space Station, CERN is an example of humanity putting politics aside and collaborating for a meaningful cause. It is an amazing feat of ingenuity and engineering, that akin to the historic technological achievement in construction of the Giza Pyramid complex. The millions of components and materials that are manufactured around the world and then transported to site where they are used to construct huge-scale machines that offer an unprecedented level of functional precision are stunning. There are literally hundreds of synchronized engineers and technicians developing, building, testing, and maintaining these machines.
Everything started at the moment of the Big Bang, 13.8 billion years ago. Time and space begin when a tiny point full of energy starts expanding at an incredible rate. An unimaginable amount of energy transforms into matter and antimatter. But shortly after, all antimatter has disappeared and only a tiny fraction of matter is left, still enough for all stars and planets in our universe. In the first 3 minutes, protons and neutrons form the lightest nuclei, while the universe continues to expand and to cool down. But it takes almost 400,000 years until hydrogen and helium atoms can form. Era can still be seen today as the cosmic background radiation. Gravity begins to pull the hydrogen and helium together. Stars are born. Fusion inside the stars forms heavy nuclei, the base of life. and these building blocks are thrown into space when stars die in giant explosions. After 9 billion years, gravity pulls some of these remnants together to form our solar system with our planet Earth, where evolution gives rise to life, intelligence, and consciousness. We understand the primordial state of matter before protons and neutrons formed. Will we find the reason why antimatter and matter did not destroy each other completely? Will we find the particles that make up the mysterious dark matter? The discovery of the Higgs boson has proven the existence of the bright angular Higgs field that gives mass to all particles. Will its study reveal any new phenomena? And will it tell us more about dark energy? The LHC will bring us closer to an understanding of our universe.
On a site in Meyrin, a small village near Geneva, work for the new laboratory begins. Within a year, the farmland is transformed into a large complex of workshops, offices and buildings to house the new accelerators. The 5-meter thick walls of the Cyclotron building soon emerge. While the different parts of the new accelerators are manufactured in several European countries. The Cyclotron's magnet coils require particular care to pass through some of the Swiss villages on their way to Meyrin. As components arrive, they are assembled with great precision. Everything starts to take shape. The Cyclotron emerges, piece by piece. Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the Cyclotron is ready. and CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with the target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. Two D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after one half turn. Meanwhile, the radio frequency generator reverses the polarity between the two electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a half turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin. 1967, a new idea takes shape called ISOL, an isotope separation device. Protons from the synchrocyclotron collide with target nuclei that are split into short-lived fragments, which are then rapidly scrutinized in experiments. The study of such short-lived nuclei with too many or too few neutrons helps to understand how heavy elements are produced in exploding stars. The synchrocyclotron accelerates its last beams in December 1990. After 33 years of an exceptionally long and successful career, the SC is retired. Following the synchrocyclotron's construction, CERN built bigger and bigger accelerators. The proton synchrotron, the intersecting storage rings, the superproton synchrotron, the large electron-positron collider, and the Large Hadron Collider. Many important achievements were made, some of them being rewarded with the Nobel Prize. The drift chamber, which revolutionized particle detection. The cooling of particle beams. The discovery of the carriers of the weak interaction. And the Higgs boson, which proves the existence of the Brown-Englert Higgs field. In 1989, Tim Berners-Lee, while working at CERN, created the World Wide Web, which has since changed our world forever. The Large Hadron Collider will continue to run at higher energy and higher intensity, with more than 11,000 scientists from over 100 nationalities, hoping for new insights into the secrets of the universe.
I think that the curiosity and the need to do research is inside is a part of our humanity, so there will be always a CERN. So there will be certainly a future.
What started once as a vision for European science has grown into a unique model for global scientific and technological collaboration. CERN demonstrates how science can unite nations and contribute to a better world.
The elementary particle are the smallest object that we know. their dimension is smaller than 10 to the minus 16 centimeter. Are you familiar with what I'm saying? 0,15 zeros to 1. The elementary particles are smaller. Where these elementary particles have been found, three of them are the constituent of everything that is around us. You know that we are made by atoms. The atom is made by electrons that are moving around the nucleus. The electrons are an example of elementary particles. The nucleus is done by protons and neutrons. The protons and neutrons are not elementary particles because they are too big. They are made by the quarks up and down. These are elementary particles. So 3 of these 30 elementary particles belongs to everything that has to do with everything that is around us. Many of these elementary particles have been discovered studying the cosmic rays. You know what is a cosmic ray? It's an object coming from space. Why is it so important to study this object? Why you are here? The answer is that we pretend to better understand our universe, the world that is around us, studying this small object.
Next we visit the Royal Observatory in London, UK. We talked to astronomer Anna Ross about extreme environments in space and an attempt to understand what to expect and prepare for as we begin to experience similar climatic conditions locally within the terrestrial context. Anna helps us raise awareness that because the tools and technologies used to observe and analyze space do so from a distance, it would therefore be inefficient and uneconomic as direct replacements. However, the collated data and devices themselves may inform design of instruments and systems specific for terrestrial parameters and technical requirements. The consistent challenge of cosmic radiation remains. Aside of constructing extremely thick shells in terms of structure, canopies, walls, is there a material that can protect against the detrimental effects? And is that even the right question? That's where I was trying to lead into, okay, the extreme environments, you know, in space, so like the moon, Mars, and yeah.
Okay, cool.
All right.
So, my name is Anna Ross, and I'm one of the astronomers here at the Royal Observatory. I have come straight from studying. I did my undergraduate degree in astrophysics a few years ago, and after that I did a master's in sort of space engineering, so hopefully more applicable to the architecture side of things, which is why you're particularly talking to me. So when you're looking at other planets and space in general, the main things you want to be concerned with is obviously temperature is a major factor. So obviously the general trend is the further you get from the sun, the colder it gets. So Mars is a lot colder than the Earth. Its average temperatures are like minus 60 degrees. Another thing that affects temperature is how much atmosphere a planet has. So again, Mars has quite a thin atmosphere, so it doesn't retain heat as well, so another reason why it's colder. The Moon also has basically no atmosphere at all, so even though it's kind of the same distance from the Sun as the Earth, it can't maintain its temperature all the way around, it has no way of keeping that heat in, so very cold at night, very hot during the day. I believe it goes down to about minus 127, nearer the equator, and up to 173 degrees during the day. There are places on the Moon that get a lot colder because there's permanently shadowed regions that never see the sun, such as the poles and some craters that have high ridges and deep shadows. So lots of very cold places on the Moon, but also very hot. So yeah, temperature is a big one. Other things to be concerned with is radiation. So out in space, there's two main types of radiation: radiation from the sun and background cosmic radiation. So on Earth, we're protected from solar radiation by our magnetic field. Mars and the Moon are both very similar in that they don't really have a magnetic field, so nothing to protect from any of that. If you're looking in space to put a spaceship or anything out there, solar radiation is quite easy to protect from just by normal spaceship materials, nothing too extreme, just metals, that kind of thing. But galactic radiation, cosmic radiation, is more of an issue. Our atmosphere is the one that protects us here on Earth from that. But again, as I said before, the Moon and Mars don't really have any atmosphere or much thinner, and that's a lot harder to protect from. Mainly because the way it works is that when it hits a substance, that radiation, it kind of knocks into the atoms that make up that substance and put out secondary radiation, and that is the radiation that is really dangerous, particularly for astronauts, because if that radiation hits your skin, then it's kind of not very good to have secondary radiation going through your body. One of the big causes of cancer in astronauts, things like that. So that's an area that is less well known as how to protect from that. So the proposed solutions at the moment are really thick shielding, which is obviously not ideal, especially if you're going off to other planets trying to launch large amounts of material. You want as light a load as you can to launch away. And there are some technologies being looked at into better materials that are thinner, but as far as I'm aware at the moment, there's no ideal solution to that. So yeah, those are some of the things. Another thing would be something called MMODs, which are micrometeoroids and orbital decay. So that's just things flying around in space, like little asteroids, little meteoroids, all those kind of things. Again, our atmosphere on Earth protects us, but the less atmosphere you have, the more you're going to be impacted. The Moon is so obvious of an example of somewhere, because obviously you can see all the craters, even from Earth with your eyes. You can see just how many craters are all over the surface, so that is a big problem. Gravity as well, I guess. So we have evolved as humans for our Earth-like gravity. Other planets, depending on how big they are, smaller planets have less gravity, and the Moon is even smaller again, so that's about 17% of the gravity. The more time you're in microgravity, the weaker your muscles get. That's why astronauts in space have to exercise for at least an hour every day, very intensely. And even then, as soon as they come back to Earth, they can't walk because they can't even just stand up again. So yeah, that's quite a big problem. So I guess the main lifestyle change would be the amount of exercise you have to do. At the moment, because we only have regular astronauts in Earth orbit, it's not as different because it's still near to the Earth. We've got a lot of protection from some things because, well, we're at the right temperature and all these sort of things. As we go further away, there'll be sort of more things to deal with. It's quite likely that if we have massive amounts of solar radiation, because the sun goes through solar cycles, so sometimes it'll be really active and a lot of that radiation will be going. You may need to sort of build storm shelters and stuff sort of to go and hide into for those times when it's particularly bad. From an astronomy point of view, the best thing that we can look at is actually Venus. So Venus has like a really thick atmosphere that is mostly made of carbon dioxide, and because of that it has a runaway greenhouse effect, much like we think may happen on Earth. So we do think that maybe a few billion years ago Venus was much more similar to Earth. It even had sort of, perhaps it might have had water and stuff like that. Obviously it being closer to the sun anyway, I think we don't think it ever had actual ice caps that would melt to increase the amount of water, but instead it heated up and then those oceans evaporated. So not 100% the same, but sort of the most equivalent really that we have planet-wise to look at. We haven't really done successful missions to Venus, so I believe the longest lasting probe that ever landed on the surface of Venus only lasted for like 127 minutes before it was completely destroyed. But there's other things in Venus's atmosphere that could have done that, not just sort of the kind of climate change aspects that we're going to have on Earth. So Venus has sort of a layer of sulfuric acid in the atmosphere, so acid rain will destroy it. There's a lot of pressure because it's extremely thick atmosphere. Sort of standing on the surface is the same as receiving about the same pressure as if you were 900 meters underwater. Basically, just don't visit Venus. It's not nice at all. But yeah, temperatures are very hot indeed. I think the average surface temperature is like 462 degrees Celsius, so very hot. Yeah, so naturally it would have been hotter, but that runaway greenhouse effect is what may happen on Earth and make it perhaps not quite that hot because it's a bit further, but yeah, the thick atmospheres keep in all that heat and make it hotter and hotter. In terms of measuring temperatures on other planets, we use something called a pyranometer, and what that does is it measures the amount of infrared radiation that you get from a planet, because that's how you sort of see heat, if that makes sense. Sort of, it's a different kind of light and shows how the heat is being perceived. So you can just measure the amount of infrared radiation a planet is emitting, and there's sort of some equations that you can use to work backwards and work out what temperature that corresponds to. In terms of chemicals in the atmospheres of planets, or if they have an atmosphere at all, we use spectrometers. So they look at the full rainbow of colours that you receive from a planet. They sort of split it up into that rainbow, and then there's a couple of different kinds. It's either an emission or absorption spectra. They're sort of the opposite. If it was an emission spectra, then you'd see lots of dark lines where the colours were missing, and that meant that a particular element was absorbing those particular wavelengths of light. And each element of the periodic table has a different sort of fingerprint, if you will, so it absorbs different places, so you can tell what elements are in that atmosphere. So for sort of general information about the climate of planets, I'd always recommend the NASA website. That's probably the most up-to-date, the most easy to use. ESA has one too.
That's great. Thank you very much.
That's okay. I hope I answered your questions okay.
Next we visit the government organisations at the Harwell campus in Oxford, UK. This is a place where you can learn about the space industry, science, technology, engineering, mathematics, and design using space technology and data to solve challenges across the Earth. We talked to Satellite Applications Catapult team, Joel Freeman, who's the head of the Center Design, about Earth application of space technology and data, as well as design process, the space race, service, and the disruptive age. Joel helps us identify that, in terms of utilizing satellites in a prudent way within the built environment, we can look at it in stages. Satellites can help us select a site to develop for specific reasons. We can track and analyze patterns of weather. How often does the location flood? Is there subsidence and ground movement with positioned reflectors? Much like the fixed node points that can be pinpointed from space and help measure deformation. We can monitor traffic flow, pollution levels, urban expansion. We can observe which surfaces receive most daylight if you wanted to harness solar energy. Or if you want to grow nutritious crops that require specific climate, soil conditions, certain altitude, you can search for that area with those qualities. You can test and analyze your specific site with regards to seasons, where there is most light and what plants may grow in that zone. A useful precedent to review is the NHS Healthy New Towns guidance. Joel noted, say if the doctor diagnosis states you need to be more active. You have a device with an application that tracks your movement. Can there be incentive to be more active? You can cover a certain distance and you can get discount on healthy foods. Now you have further incentive to lead an active life and consume high quality nutrition. Underpinned by satellite technology that is accurate within 1 millimeter tolerance in the Z-axis and approximately 300 by 300 millimeter square resolution pixel as a spatial graphic, true as of 2018. Evidently, if you make data and technology a resource and ultimately a tool that is accessible to people, meaning that you do not have to be an expert to use it or have to code it, and it works as an add-on or a plug-in into your specialty of consultation, then we will experience profound ingenuity and shifts will take place. Inventions, solutions will pop up exponentially.
Okay, so my name is Joel Freedman. I'm the head of user-centered design at the Satellite Applications Catapult. My background is in product design and mechanical engineering. The course I studied and then followed on with a master's was a split between straight mechanical engineering, just how things work, how to understand materials, how to kind of build stuff, and product design, which I guess was trying to tell you what to build. So the product design side was very much focused on understanding people, understanding opportunities, coming from a point of view that product design is is kind of cutthroat in that you can design something and people will either buy it or they won't, and if they don't, it fails. What gives you your competitive edge is understanding why someone would buy your product over someone else's. So to get that, you need to understand people, and the method that we were taught was known as, referred to as human-centered design. That really is around putting people at the center of your design process and basing your design on an understanding of them. So who are they? What do they do in their life? What are their habits? What are the struggles they have? What are the motivations they have? And by starting to understand how to get that information from interviewing, from observing, and then starting to lay it out, synthesize it and categorize it, visualize it in different ways, you can start to see insights about that person where there are opportunities for some sort of product that will really fit into their lives and really help them with their problems. So that was the course I did. I wasn't really sure what I would do with it. I just knew that I wanted to my job to be getting paid to come up with ideas. Actually, that was, when I went to university, that's what I wanted. So now I'm working at the Catapult, the Satellite Applications Catapult, which is one of a number of technology research innovation centres across the UK. They were set up by the government. The first ones were set up about 6 years ago, in areas where the government identified there was big potential for future economic growth. And a study was done to look at how the UK could foster this type of innovation and support the commercialization of it. And they looked at a model in Germany called the Fraunhofer Institutes and saw that if they could identify these key areas of technology and set up centers where there's expertise of technical, business, design and links to academia and industry, they could create an environment that could support the growth of that sector. They were set up to address initially two kind of key gaps, barriers to growth in those areas. The first was identified as a barrier of the commercialization of academic research. So the UK traditionally is very strong with academic research, but not as good actually turning that into real commercial opportunities. The second was, how do you go from being a small, medium enterprise, or an SME, we'd call them, to scaling up to being a large company? Part of that is around understanding how you develop a product to be suitable for a larger market. Another part is finding that market, but another part is understanding how to run a business that size as well. So it's not just a case that you could be a small company and all of a sudden you hit this big market and you've got like millions of pounds of orders and you just carry on. There's a whole load of changes that would have to happen. And so the catapults are set up to partly research the kind of cutting edge of technology and partly support people who could feed into that and turn that technology into something commercially sustainable. So this particular catapult, the Satellite Applications Catapult, is focused on applications of satellite technology. How can space technology be useful here on Earth? Space technology is a really interesting industry to be part of, because although the space industry is an industry in its own right, it's actually an enabler for countless other industries. Satellites can be used to broadcast information, as everyone knows. They can be used to help you know where you're going. They can also be used for agriculture. They can be used for disaster recovery and monitoring. They can be used for climate change adaptation, for building future cities, for monitoring transport links, for monitoring infrastructure. The amount of different industries that are enabled by satellites are countless, really. And so what that means is working here is extremely varied and extremely interesting, and is one of the reasons that I love it. We get to look at how this technology can be applied to solve challenges that are not just in the UK but are global as well. Satellite technology can be roughly split into three buckets. The first is communication, so passing data all around the world, creating connectivity everywhere really, from Internet of Things devices sending very small bits of information. You know, it could be a sensor on a plant in the middle of the desert telling you how much rain there's been, versus streaming video, Skyping with your family while you are in your autonomous vehicle driving across the UK as well. So the range of communication, it's really about giving us access to information wherever we are. The second bucket is navigation. So understanding, or positioning really, understanding where on Earth we are and where other things are. You know, that's something that is so fundamental now, we almost take for granted, that we can position ourselves, that we can type in the name of a shop on Google and know exactly where it is. Doesn't matter what country it's in. That ability to know where things are and know where you are is hugely powerful. And there's another level to it, which is not just where things are, but how they're moving as well. So by seeing how something's moving, you can start to infer characteristics about its behavior. So for example, we have a demonstrator that was a project that turned into a commercial service, which is focused on illegal, unreported and unregulated fishing. It's a huge problem around the world. The ocean is very big, it's very difficult to know what boats are doing. But actually, there is a system on boats that is mainly for identification and collision avoidance called AIS, and it can be tracked from space. So if a boat has its AIS on, broadcasting who it is, you can see where it's going. And so you can look at, okay, well here's an area that's protected and here's a boat going through it. And if I look at the way it's moving, based on how the system's been trained, it knows that, well actually that is very indicative of tuna fishing, or two boats moving together is very indicative of a transshipment as well. So a system can start to flag up areas of suspicious activity. Even, you know, there was a boat heading towards this protected area and it turned off its AIS and all of a sudden it disappeared and then it turned back on over here. There's certain things you can start to infer. So that's the movement, position, navigation. And the last is Earth observation, remote sensing. To me, that's one of the most mind-blowing areas, because you're taking sensors that are looking at the world like cameras, and from a picture that could be kilometers across, being able to look at like the health of a plant based on the amount of green light that's reflected back. You could be looking at where there's been a change in the landscape due to millimeters of height difference. You can look at the chemicals in the atmosphere, pollution in water. Anything you can sense on Earth, you can likely try and sense on a bigger scale from space. And that becomes really interesting as well when you start adding other technologies like computer vision and machine learning as well. So if you can train a computer to start looking for certain patterns, certain features, and you're getting this global view of how things are changing, you can very quickly set up alerts to warn you of natural disasters, of buildings that might collapse, of areas where maybe there's people who are, I don't know, in need of help. They're lost at sea, they're moving around in a certain way, they're polluting a river. There's all sorts of things you can do with it, and it's kind of infinite and endless in a really wonderful way. So that's the remote sensing side of it as well. So, okay, one question then is, you have these technologies, so how does human-centered design or user-centered design actually fit into that? We can say, I think that if I compare an image today with an image yesterday of a forest, I can see whether there's any trees that have been removed. So therefore, I think that you could use satellites to solve a problem of deforestation, illegal logging. Okay, it's a good premise. But going from, I think I can do this with this technology, to I've developed a service that people are using, there's a big gap. And one of the first parts of going through that process is to understand who it's for, who actually is your user. To design any sort of service, you need to understand who is going to use it. What is it they're doing now? What is it that is not working about what they're doing now? What is the actual information they need to see to be useful? You know, are there lots of different people tracking these trees? You know, there might be rangers on the ground, there might be government organizations in a different part of the country, there could be NGOs in another part of the world also looking at this. So who's doing what, and how can you make sure that what you're creating is not just going to disrupt people's daily activities necessarily, but it will fit into it. Being disruptive is great. Disruptive technology is good. Disrupting people is not so good. What you want from your applications is that they're smooth, is that they're almost instinctual, and that they kind of know what you're going to want to do before you do it. And that doesn't happen by accident. That happens through really understanding what it is people are going to want to try and achieve, and then turning that into a set of specifications and designs that can then be given to the technical people to say, okay, we know what we need to do, we know what they want, let's go and build it. So part of it is our team is a research team. We go and talk to different users around the world to understand what their challenges are, and identify the areas where satellite technology could solve them. The next bit is then we take that information, working with technical teams and business teams, and we come up with some concepts. Now it's really important that the business team's there as well, because you need to have this kind of trilogy of technical, business and design. So it needs to work technically, yep. It needs to solve people's problems, they need to want to use it, but also it needs to be a sustainable business, and needs a sustainable business model. You can't just say, I've got this great technology, they really want it, I'm going to charge like £10 million for it, because no one's going to buy it. But likewise, you could have a great technology that's like super cheap and no one cares about it, so that's not going to work either. So it's really important that from the beginning we have these multidisciplinary teams together, and you're looking at not just what is the problem that someone has, but what is the value of that problem to them. And you can kind of quantify that in a number of ways. You know, you can look at, I'm going to design a solution for you. If you're going to pay for that, either it needs to save you some money that you're already spending, or it needs to help you generate more money. As long as the cost of my solution doesn't outweigh any of those, then we've got something good going on. So we get those teams together, we conduct research, we then start to put together some ideas of, okay, what might this look like? What sort of technology could it use? Where could the data come from? How much might it cost? And we put together some pretty basic kind of sketches, models, and we take them to people, and we get their opinion on them. We say, look, does this make sense? Does this look like it would solve your problem? Is there more information you'd need? Would you pay for this information? Who else do you think would benefit from it? And very early on, start to iterate the idea based on that user feedback, which means that we don't just go away, spend hundreds, thousands, millions developing something, and then go, oh, here you go, and you're like, it's not quite what I wanted. We're constantly checking and iterating our designs, which is a kind of course correction. Because when it comes to design and development, you're really looking at a kind of costs committed versus costs incurred model. So by that, you know, the decisions you make early on commit you to costs. If I'm designing a chair for you, and at some point I say it kind of has to be gold, I think it's going to be gold, and I put that down, I'm kind of committed now to paying a lot of money to make that chair. Now, if early on someone goes, sorry, why is it gold? And I'm like, well, I just thought it would be great. And anyway, we go through that conversation, and I go, okay, maybe we just like spray paint it gold instead. That's fine. We've now saved that money. If I don't have that conversation till the end, it's a little late for that. It's really easy to change your mind and make decisions early on in the process. So the more you can have those conversations, the more you can iterate and play with different ideas early to land on something suitable, the better your design will be. So part of what we do is the development of applications, from research to design to testing. Another part of what we do is taking that overall process and advising companies on how to do it. So not doing it ourselves, but working with startup companies, working with academics, getting a designer, a business strategist, and a technical person in a room with a business, and helping them to really think about who their customer is, think about their product and their service, and take them through that same process based on our learnings, so that they can get to a point where they have a really robust, scalable, sustainable business model. So we do that for small companies. We do it with big companies as well. Part of our methods normally involve bringing together lots of different people, different stakeholders, and getting them to think creatively around their problems, their challenges. And these sort of co-creation sessions are important for a number of reasons. One of them is because you get really much more interesting and unique ideas when you get lots of different types of expertise together, because they will all think of something that you wouldn't, and so that gives you a really rich environment for innovation. Another is that if you involve someone in the process of designing something, they have some ownership over it. They're more likely to use it, and they're more likely to defend it. And so that's really important from a point of view of developing applications and services.
Transitioning to Mike Curtis-Rouse, the lead manufacturer in technologies. We talk about space technologies, additive manufacturing, on-site construction on other planets, and materiality. Mike noted that whilst the space industry is highly competitive, there are many common challenges that can be resolved through collaboration and sharing of ideas. Biomimetics, in terms of learning from nature, of the living world, is crucial. For example, it is prudent to look at the structural properties of trees, which will endure long after we're gone. Notice large rocks and boulders that weigh hundreds of tons, that have been around for multiple millions of years, because they weather the environment. The placement and how it emerges in terms of its constitution, whether it is metamorphic or igneous rock, the structural properties and the chemistry can inform how we construct more durable materials. Keep an open mind and ask questions. After all, curiosity is what makes us discover abstract concepts that manifest themselves. Like if we stretch and relax wires in a torsional device, we can generate electricity whilst rotating an object. That is a practical idea that develops in stages.
Okay, so my name is Mike Curtis-Rouse. I'm the lead manufacturing technologist for the satellite applications Catapult. The Catapults are a series of organisations which were established about 5 years ago in the UK. They are basically designed to facilitate and accelerate commercial innovation, particularly taking technologies at the academic level to an extent, levels we refer to as technology readiness levels, and the TRLs run from 0 to 9. They were a NASA-derived standard in the 1960s. TRL 0 is basically a concept, a thought. Could I lift myself by my shoelaces? TRL9 is I've managed to lift myself by my shoelaces and commercialize it, and you can now buy it in the shops. Unlikely scenario, however. So the Catapult's focus on taking technology from a technology readiness level of typically 4 all the way through to 6, and this is what we typically call the Valley of Death. This is where technology ideas, innovation, science, manufacturing, other areas like that tend to fall over. Universities and other smaller organizations are good at generating it. Sometimes it doesn't make that transition through the Valley of Death into industry. So the catapults are there to help facilitate that. And the catapults cover a whole variety of areas. They cover everything from renewable energy to precision medicine to high value manufacturing. And in the case of my catapult, satellite applications. Now, in the past, the satellite applications catapult was focused very heavily on what we call downstream applications. And that's basically considering a spacecraft, a satellite, taking data from that spacecraft and utilizing that data for applications on Earth. Now, that might be communications, faster, better internet signals, might be telephones in terms of mobile coverage, it might be imaging in terms of I want to see how my crops are developing over the course of the year, or it might be something, for example, like recently like the collapsing dams in Brazil, about how do we do disaster recovery. Wide applications, and of course you can never forget global positioning, because without GPS and the variety of networks which provide GPS, most of us probably wouldn't be able to get home or let alone to work. So big areas like that. That's what we call downstream application. The other side of that though is upstream, and upstream is where I focus. Upstream is basically about how do we get spacecraft into space. So are we using a launch vehicle like a rocket? Are we using a future conceptual launch vehicle like a space plane? How do we communicate from the ground? So it's a ground-based antenna, to how do we manufacture spacecraft which actually do those jobs, the actual physical satellites. And then even to a little further extent, just pushing a little bit further into the more blue sky area of what else can we do in space? What about in-orbit manufacturing? Not necessarily just building satellites in space, but for example, manufacturing things like pharmaceutics. We can build better cancer drugs in space because we have a low gravity environment. Crystalline structures form better and faster, meaning that it's opening up the opportunity to create a whole variety and a whole wealth of new medicines for a whole variety of conditions, building better materials, building better electronics. So there's some really interesting applications about what can we make in space. And then if you really want to start looking to the future, what do we do beyond Earth? We're going back to the moon. We'll certainly be on the moon within 10 years. There's a good probability we'll be in Mars within 20. Where next? Big options. However, let's focus a little bit down to where we are today. So today we're in what we call new space. New space is a transition from old space. Old space was the domain of the large space agencies and the large multinational aerospace companies, NASA, the European Space Agency, companies like Lockheed, Boeing, Northrop Grumman, Airbus. Those companies have defined how space is, and they're based on those launch systems like Ariane 5, the Space Shuttle, Atlas, Delta, a whole variety of other launch vehicles, and big satellites. Satellites typically are the size of anything from a small mini car to the size of a bus. They weigh anything from a few kilos to hundreds of kilos, in some cases many tons. New space is about cheaper, better, faster. It's complete dichotomy to old space. How are we going to do things differently? And it's about ultimately cost. Space is expensive. When the space shuttle launched, each launch cost in the region of 350 to 500 million. That's not sustainable, bearing in mind for that launch you can maybe put a maximum of 20 tons in orbit. So rockets are cheaper, but even nonetheless, effectively a Falcon 9, one of the SpaceX's conventional launch vehicles, still cost in the region of $60 to $7 million per launch. So that's a lot. I mean, that number's come down by a factor of 5, but it's still a lot. So space is about building things smaller, smarter, quicker, and new space is very much about building small spacecraft. So I said earlier about spacecraft being big. New space there's a big focus on how do we make spacecraft smaller, but how do we still make them effectively functional, useful, effective? And the ways we do that are through a variety of new design philosophies, looking at disruptive technologies where we look into other markets, high performance motorsport engineering, for example, new forms of composites, new forms of metal, advanced alloy development. We even look to biology. How do we build complex cellular structures which can absorb impact or absorb radiation? So can we learn from nature in terms of how we build something that is fundamentally not even remotely related to nature? And by example, effectively, this is effectively what we would call a picosat. It's a very small spacecraft, and this is actually a physical spacecraft. It could, if we chose to, launch it. Like most spacecraft, it has a series of attributes. This one is about imaging. It has fundamentally a small camera on the front. It has solar panels on a variety of sides which generate energy, because at the end of the day, if you don't have power, your battery's going to run out and you can't do anything. Importantly, if you're going to take pictures and you're going to have power, you need to tell someone about it, otherwise you've got a spacecraft which fundamentally does nothing. So the rather elegant tape measure on the back, which actually serves a very useful purpose. This is the antenna which allows the ground station on Earth to communicate to the spacecraft. And often we are asked, why would you use a tape measure on your spacecraft? Well, the reality is actually it's cheaper to buy a tape measure and cut it to size, and it has conveniently the markings on it so we can calculate the frequency for the spacecraft, than it is to buy an equivalent length of metal, mark it up and attach it. So you could argue this is fundamentally disruptive space. Maybe not necessarily envisaging where B&Q would help us build better satellites, but the reality is that actually right now that approach to mass manufacturing allows us to do exactly that. So a picosat like this is useful, but it's not necessarily that useful. It's too small because it doesn't have enough solar panels on it, doesn't have enough effectively computing power on board to do things, and in reality it can't really position itself either. It has no thrusters, no propulsion. Spacecraft, if they're looking towards the Earth, need to be able to be orientated towards the Earth so they can stay looking at what they're looking at. So we tend to use a standard for small satellites known as CubeSats. And CubeSats is a term that many people probably would have heard bandied around. It's becoming fairly common. But fundamentally a CubeSat is literally a spacecraft which is about 10 centimeters to a side, effectively a cube, and weighs in the region of about 1.3 kilos. So it's a small satellite, but it's big enough that it can do something. And typically what we refer to CubeSats are, this is what we call a 1U. So this is the CubeSat, and this is what we call a stack. And the stack is where we basically attach the electrical boards inside, the processors, the battery, the solar cells, additional communications. That lives inside the spacecraft. So this is a 1U spacecraft, but we can also have a 2U, which is, by extension, two 1Us connected together, or a 3U, quite easily jumping on, 3 stacked together. A 3U spacecraft or a 6U spacecraft, which is effectively a 2x3 configuration, is significantly more useful than just a 1U. Why? Because you can have more solar on it. The more solar you have, the more power you have, and equally, by extension of that, the more space you have to do things. So right now, there are a whole variety of small CubeSats of that configuration in orbit around the Earth, doing a whole variety of functions. One of them includes, for example, the planet constellation. And a constellation is basically a collection of spacecraft. It's a new approach to how do we build spacecraft and what do we do with spacecraft. So if we go smaller and we want to build more spacecraft, then the reality is that we put them together in something we call a constellation, because the spacecraft being smaller mean they can do less compared to a much larger spacecraft. So if we put many spacecraft together in a constellation, they can still perform the same function as a larger spacecraft. The advantage is we can build them faster, we can build them cheaper, we can probably launch them faster, which means that the time it takes from effectively a project starting to the time you're actually getting commercial benefit is far, far quicker. And critically, what's most important is it means if something goes wrong, and space is still fundamentally a dangerous environment. Rockets don't explode that often, but they still do. The chances of a rocket exploding is about 1 in 500, so relatively high when you think about the equivalent of being hit by a car is about 1 in 11 million. So spacecraft have a fairly precarious life. Launching a spacecraft is a pretty precarious experience. A launch of a spacecraft is pretty much the equivalent of the experience that a human would have in terms of effectively being born. It's a traumatic, terrifying entry to the world. And for a spacecraft, it's a traumatic, terrifying exit from the world. And when that happens, things go wrong. And one of the reasons things go wrong is about connections. So if I pick up, for example, this spacecraft, now this one is still basically a small picosat, has nothing in it. What will eventually end up in it are a series of boards like this. So this is a processing board. Actually, it's quite similar to a processing board that you might find in your mobile phone. So it has a socket here for a SIM card, for communication. Not that we use SIM cards in space. This is for testing. It also has a processing board here, and then it has connectors at the top and bottom, which will allow us to stack these boards together to effectively form, as I referred earlier, the stack in this spacecraft. So this is a larger version of effectively that. Now the problem with this is that these are fundamentally connectors. And every time you connect something together, there's always the risk that motion or acceleration may dislodge it. So we go back to talking about launching. You launch a spacecraft and it starts to shake. It's a phenomenally violent experience because we're taking an object which is basically stationary and we're accelerating it to moving in excess of 5 to 6 kilometers a second to break away from the Earth. That's a pretty terrifying experience. It doesn't matter whether you're a human or you're a very small satellite. It's generally pretty terrifying. So you can imagine that effectively this thing is shaking backwards and forwards violently, and the chance of it dislodging and separating, or a solder joint breaking, or a cable coming loose is actually relatively high. Now, we engineer spacecraft, big spacecraft, to fundamentally avoid that by testing them again and again in a variety of conditions. We simulate the conditions of space, hot and cold, we simulate vibration, we simulate shock. When a spacecraft separates from its various stages, which are using effectively different rocket engines to get it higher and higher, it's basically separated with explosives. So there's a loud bang and suddenly the spacecraft comes apart. All of these shocks go through this spacecraft. Big spacecraft get tested a lot. Smaller spacecraft get tested less because of the cost of it. And the cost effect. So we're doing less testing on small spacecraft, yet they're still going to experience the same potential shocks. So how do we mitigate against that? And there were two ways. One, well, technically there are three. One, you do more testing, but testing is expensive. It delays the amount of time it takes to get something into space. So the two approaches are: one, build more spacecraft. So if you launch one and it fails, you've got enough in your constellation and they're cheap enough to launch another one that it doesn't affect your overall functionality of what those spacecraft are doing. Or two, you look at new technologies which allow you to join materials together without effectively joining them. And this is where technologies which the rather overly used term 3D printing, or as we refer to in the industrial environment, additive manufacturing, come in. So the ability to take structures, for example, and join, there we go. So the ability to take structures together like these, so these are dampers for spacecraft. So for example, the base of this would effectively sit on the top of the rocket, and then we would attach the small spacecraft via its docking clamp to the top. So any vibration and motion is basically reduced. So effectively this is dampening, in the same way that you have suspension in a car to remove the bumps as you're driving and make the experience of driving through a very potholy road slightly more palatable. The same way we do with spacecraft is we put in dampers to reduce the amount of vibration. And this part, for example, here is made using additive manufacturing. So like most processes, it's built layer by layer by layer. And by building it as one part, as opposed to a conventional damper which might be built in many parts, we remove that risk of failure. So this is one part. It can only move in these directions. We can rotate it 90 degrees, so we could build one on top of another. But because it doesn't have any joins in it, because it's not welded together, because it's not screwed or clamped or even nailed, though I don't think you find nails in spacecraft generally, there's a very low risk that this will actually physically come apart. So building things as one part is super attractive, and that's why technologies like additive manufacturing are becoming very, very common to space. And at the same time, additive manufacturing is good for making low volume components. If you're going to build 1 million Coke cans, for example, you're not going to use additive manufacturing. It doesn't scale. But if you're going to build 5,000 small spacecraft where you're trying to reduce the overall component count, then additive manufacturing, despite being a relatively expensive technology to utilize, is an ideal technology to utilize. It scales very well. And the other advantage of it is that you can take a component like this, design it, build it at this level and say, you know what, actually I'd rather it was smaller. So then you scale it. So then you can basically just build it again, and now you have something which is exactly the same. You have changed nothing other than you have told the system which is building it to effectively build it at 1/4 of the scale. So it performs in exactly the same way, the materials have the same properties, and you have the same performance throughout. So that becomes phenomenally attractive when you're trying to build complex objects, complex spacecraft. And that extends going beyond just, for example, spacecraft. That extends the new generation of launch vehicles we're seeing. So the ubiquitous, effectively, SpaceX Falcon 9, very common, or comparatively common for a rocket, very reliable, and has been built using a variety of new launch technologies and new manufacturing technologies. At the same time, though, we're seeing a multitude of new launch companies, some in the UK. So currently, right now, there's 13 small companies of various scales building launch vehicles, aspiring to make access to space cheaper. And then worldwide, there's at least another 120. So suddenly, whereas 5 years ago, there were maybe a dozen launch companies, all predominantly large aerospace companies or government organizations. Now suddenly we've gone up by order of magnitude. 120, 130 is growing on basically a monthly basis. We're seeing more of these launch companies coming out and developing new capabilities, saying, actually we're going to build rocket engines like this, actually we're going to go with this configuration. Most of them will fail. Rockets are complicated. Well, actually no, rockets are not complicated things. Rockets are really simple, but building rockets which are reliable and which don't explode on a regular basis is really hard. And then doing that and building that cost effectively is even harder. So again, we see technologies like additive manufacturing, the ability to use advanced materials, dedicated specific alloys, new types of plastics. These are key technologies which allow us to build better systems. So again, another additively manufactured component. It looks incredibly simple fundamentally. It's square at one end and it's round at the other. You could argue, well, that's a pretty easy thing to make. But if I wanted to make this using what we would term subtractive manufacture, then that's effectively where we're taking away material to build up the part we want. I could machine this, so I could take a block of, for example, plastic, or take a block of steel, and I could machine. But if you think about it, it would have to be larger than this object, and also in the middle, all this material has to come out. So all I'm doing basically is taking a large object and reducing it down to end up with a smaller object. Or, by extension of that, I could take a flat sheet material like plastic or stainless steel, and I could basically machine it, bend it, and weld it into a shape. But I go back to my earlier point. If we were effectively machining this and assembling it, this would be effectively a join line, this would be a join line, this up here would be another join line. So what happens is I end up with multiple joins, welds and seams. All, from a launch perspective, are effectively failure points. So by building it like this, I have one component, it's built quickly, it's built efficiently, it's built without those effectively inherent failure points. So these sort of structures are ideal for launch vehicles. And this is part of the ducting component, so this is part of environmental ducting. It's not particularly exciting, it's not a nozzle for a rocket engine, it's made of a plastic called Ultem, which is very temperature stable in space. It doesn't outgas, so we don't see trapped gases. When you make something, you see gas trapped inside structures. We don't see those gases leave the structure, because when they leave, they can leave rather explosively in the vacuum of space, which can render a part effectively fundamentally broken. But at the same time, it's also tolerant to UV light, and that's important as well. So you can build structures like this, and as I say, not exciting. You couldn't use this as a rocket nozzle, it would melt very rapidly, but you can use it for key components. And the other aspect of it is not just in terms of the manufacturing, not just in the terms of the reduction of the number of failure points, you can also optimize it for the shape. So you can take a structure which is designed to function in one way, and then you can optimize it and build it so it's much lighter. So what, by extension of that, we are increasingly seeing components like this. So this is a housing for a motor. The motor, basically, the body of the motor lives in this section, and the front of the motor protrudes out of here, and this is for basically a space-based joint on a spacecraft. We can build this basically as one component. We can do a lot of machining, or we can basically use additive manufacturing to build it. So now inside I have a bracket to mount the motor on, which is part of the lower housing, which then fits into the upper housing, and it fits seamlessly together. So where in the past this would be multiple components and would weigh probably significantly more, this is a relatively light component, yet performs exactly the same functionality. We can build it in a tenth of the time for probably a 20th of the cost, and we can reduce the overall weight by a fifth. Those factors, when you're trying to manufacture anything, if you can say from a manufacturing perspective, I'm going to build it faster, I'm going to build it better, it's going to weigh less, and it's going to cost you less, those are usually the sort of targets that really efficient and highly desirable production demands. And if you can do that, the cost of launch vehicles, the cost of spacecraft drops, because each component you're building is costing you less, yet it can still perform the same functionality. In some cases it can perform even more. And that's why these technologies are fundamentally changing how we perceive space and what we can do in space. And ultimately, if we want to go beyond our own Earth, if we want to go beyond our own moon, and we want to go beyond our own solar system, it's going to be fundamental that we take technologies like this and we adopt them in new ways. So right now what we're seeing in new space, in terms of the evolution of small satellites in orbit around the Earth, being built cheaper, quicker and faster, and they're not just being built typically by large organizations and space agencies. These small satellites are fundamentally so simple that the reality is that a group of 14-year-olds could put one together in an afternoon. Now, I'm not suggesting that 14-year-olds should build spacecraft yet, but there's nothing to prohibit effectively schools, and right now many schools and universities and private groups are building spacecraft and to an extent are launching them. Now, they're not launching them on their own launch vehicles. Owning a rocket and launching a rocket is a very different matter to building a small spacecraft, but the ability to do that and the ability to build small spacecraft and then have them launched is a great way to both attract a whole variety of new skills and new individuals into an exciting sector, grow our economy, and ensure that people with skills, or effectively people with the aspiration to have skills, have the opportunity to engage. So new space is one of these revolutionary areas which is changing a generation. It's changing how we think about technology, and it's changing people's ambitions. And that ambition to go further, faster, quicker, the much and again overly used term of the final frontier. Well, the good aspect in a way is we never get close to the final frontier, because every time we do get close, we discover that we can do something else, and we just go a little bit further.
3D printing as a method of actually building something on site.
Absolutely. So you're talking about in situ resource utilization.
Yeah.
Lovely, well-remembered acronym. So in situ resource utilization is taking the materials you might find on the moon, regolith, which is lunar soil, or on Mars, the Martian equivalent of terrestrial soil, and equivalent materials, and building structures. And absolutely, you certainly can do some of that. The slight challenge we have is every time we think that we've found the right material or the right analog to those materials, it doesn't always quite add up in the same way. And originally, one of the concepts for occupation and inhabitation of the moon was to basically use lunar regolith, melt the lunar regolith into a glassy-like substance, and basically grow your own effectively sort of hemispherical dome. The reality is that actually we've gone down various avenues, mostly driven by the space agencies like the European Space Agency, in terms of how we might do this. And then people have had an epiphany and said, well, actually, why do we want to live on the surface of the moon? Lots of radiation, small meteorite bombardments, etc., lots of dust. Why don't we go underground? So suddenly there's been a switch of, actually, maybe we don't build things on the surface, we look for a lunar cave. And lunar caves are formed effectively by the cooling of lava, as you find on Earth. In places like Iceland, you find natural caves forming where the lava is effectively cooled and left a resulting cavity behind. So the reality is I suspect future lunar bases probably will be underground. That said, we will probably almost certainly take technologies like 3D printing and utilize that to build structures to fill those spaces up, whether we're building airlocks or whether we're building actual rooms or whether we're building furniture. It seems a logical way of doing it. Mars, on the other hand, probably has caves, but we're not entirely sure. So going below ground is harder. So the reality is we will almost certainly look at a variety of initially habitats which we take with us, but at a later date it's highly likely again that we look at structures, and there's a whole variety of materials we can use on Mars, whether it's effectively the equivalent of the Martian soil going across to actually ice. So there are some 3D printers, for example, which literally are, if you imagine a rotating cannon, which effectively tracks round and round in a circle in kind of an upside down way of a normal 3D printer, which is effectively building down and building over the surface. This sprays water because the Martian atmosphere is at least -30. The water basically freezes instantaneously. So you can basically build a structure of ice which acts both as your structural walls, so it gives you strength, it gives the ability to clad it, and one of the interesting things about water is it's radiation absorbent. So Mars basically has a relatively high exposure of radiation. So one of the best ways to mitigate the exposure that astronauts on Mars will have, and future human settlers, is to use water as a barrier to absorb that radiation. So if you build effectively your ice house is both providing you with your thermal protection, and it's providing you with your radiation protection. It's providing you with some impact protection, and and at the same way as if you've ever built an igloo, for example. Being in an igloo, most people assume by default it's cold, but the reality is the ice acts as an insulator, and being in an igloo you can actually light a fire, and no, it doesn't melt your igloo. Well, it won't, as long as it's a relatively small fire. You actually stay warm. So ice is a really interesting material to utilise. The drawback is it's very hard to prototype that, because if you imagine trying to basically find an environment on Earth, even in the Antarctic, where you can basically build an ice-like structure and test it in fairly extreme conditions is pretty challenging. But the reality is if we ever want to do that on Mars, the probability is we're going to have to build some form of ice house on the Earth in the first place.
We talked to Oxford Space Systems team, Mike Lawton, the founder and CEO. Talk about the systems, materials, industries that inform design and design process, as well as environmental constraints and opportunities in space. Mike raised, whilst there are wonderful materials and technologies going into orbit, there are interesting terrestrial application options. For example, a lightweight pop-up structure that can create a safe canopy or bracing if deployed. Certain material properties in terms of composition can be exploited when activated in the strongest dimension. Imagine emergency shelters. Or if you are in a car crash and the car rolls, rather than having a heavy roll cage, install a stowed unit that is lighter, more efficient, and deploys like an airbag. Okay, digging underground and supporting the Earth from collapse. Or take advantage of the very intense ultraviolet radiation in space in combination with soft, pliable materials which become stiff when exposed to UV. So, if you have an inflatable membrane stowed incredibly small for launch, inflate it on orbit, as you do not require much air pressure to inflate it, and let the UV cure it. Then remove the air pressure, and you have a spatial intervention you can inhabit.
My name is Mike Lawton. I am the founder and CEO of Oxford Space Systems, and we are a space hardware business. We're venture capital backed, which means we have to be doing really exciting things with technology in order to secure the level of external investment that we have. And the exciting technologies we're developing are deployable structures for space. And by deployable structures, we mean things like antennas, boom systems, and deployable panels. So the problem we're trying to solve at OSS is getting large structures on orbit. And the big challenge is fitting very large structures into very small rockets. So roughly 95% of a rocket is its fuel tank, which leaves us very, very little room to get a satellite and all its plethora of deployable structures. So that means everything that we do is driven by stowage efficiency and trying to make things as light as possible. So what we look for are materials that are very, very light that we can stow in a very efficient manner. And then we need to then use design practices that allow us to use those materials in a certain way that don't compromise their physical properties, but meet all the demands of going from the Earth's surface into orbit. So even before we put a structure on orbit, we have a pretty torturous existence to get through. Just getting from the Earth's surface to orbit takes around about 45 minutes to an hour, but it's incredibly violent. So that means all these lovely exotic structures that look very delicate on orbit, unfortunately, have to survive a very, very violent start to their life. And that drives all the design principles and choice of materials that we have to make. And it's pretty crazy when you think about it. A satellite can be on orbit anywhere from 5 years up to 25 years. But what drives all that design is just 45 minutes of its life. So it's a bit like buying a car. You just want a little city car, but you can't have that. You've got to buy a car that survives the Paris-Dakar rally for 25 times. And that then is the design that we give you. So the whole idea of space design is driven just by 45 minutes at the start of life. So we have the challenge of excessive vibration, and that drives the way we put materials together and the inherent design. So they've got to be very, very vibration proof. But once we're on orbit, we then open up our satellite and our structures to a whole range of other huge design challenges. So in low Earth orbit, it's fairly benign in terms of temperature. It's not as cold as hot as people think. If you get it right, you're going to see temperatures of around about -60 to around about +60, +80. So it's not crazy, but it's a tough temperature range. We then have radiation effects, but we still enjoy a little bit of protection from the Earth's magnetic field. So it's not as intense as people think. We have astronauts in orbit on the space station. But the one effect which really drives a lot of our design is something called atomic oxygen, or ATOX. It's the last wisps of the Earth's atmosphere being broken apart by the effects of radiation. And atomic oxygen, the clue's in the name, the oxygen becomes a bit like a free radical banging around looking for something to react with. And if it gets into the sort of materials that we're designing to go on orbit, it can literally cause significant damage. So for instance, one of the materials we use on orbit is carbon fiber. Unless that's designed in a certain way, ATOX will get inside that material and shred it. It can make hard carbon fiber end up looking like tissue paper. So all these effects we need to understand and design for. And another huge challenge in space, no matter what orbit you're in, is the hard vacuum. So in mechanical design, we take things like lubricants and greases for absolute granted here terrestrially, and we have a vast exotic range of lubricants we can use. The one thing you can't use in a vacuum is a lubricant or a grease, because it instantly vaporizes. So if you've got a very expensive satellite with a very expensive camera system, the last thing you want is a thin film of grease over the lens, which means you therefore need to look at materials which are self-lubricating, for instance, things like PTFE. And we have to avoid metal-on-metal contact in a gear system, for instance, because once you're in a hard vacuum and you don't have a lubricant, we have something called cold metal welding. Metals actually get confused, if you like, when they're in precision contact with each other, and you almost get an exchange of molecules, so the metals end up welding themselves together, called cold metal welding. So we avoid metal on metal. So all these things conspire to drive choice of materials and the design techniques that we need to employ at OSS. So I mentioned the challenge of stowage efficiency. How small can we stow structures? So at OSS, we don't just design the structures, we actually design the materials ourselves to make up some of these structures. So on our team, yes, we have the usual range of thermomechanical design engineers, but we also have material scientists helping us develop our own materials. And our most mature material that we currently have on orbit that we're demonstrating is what we call a high strain composite. So most people are familiar with carbon fiber, normally a thick, rigid material. If you own a tennis racket or a fishing rod or whatever, invariably it's made of carbon fiber. So you're familiar with what we call the kinematic properties. However, we've developed a lot of intellectual property on turning this material into a material that can deploy. So we have all the advantages of carbon fiber, but now it's super flexible. We can roll and stow it in a very small volume for launch, and then on orbit we can get it to deploy and become a structure. So here it is in its most simplest form. So turning this material into a useful product, we have a very simple demonstration here. So if we contain the material in a little cassette system and put a very simple motor system around it, we turn this violent release of material into a very controlled deployment in a very, very compact, ultra lightweight deployment boom system. And what looks like a large sugar cube on the end, this is representative of a typical payload that we would fly on orbit. So if you wanted to measure the Earth's magnetic field, you would use something called a magnetometer, which looks a bit like this large sugar lump. And the reason we need it on a boom away from the spacecraft, we want to deploy it into clean space, so it's measuring the Earth's magnetic field and not the parasitic magnetic field of the spacecraft. So the further you get away, the higher the quality of your measurements. And of course we can reverse it as well. It's not just a single shot. So in this case, you can imagine we could deploy at various radii from the spacecraft and carry out a whole range of interesting scientific experiments. So this is a very, very simple demo. A more complex version of this is currently flying above us at an altitude of about 650 kilometers in low Earth orbit. And we've deployed and retracted this boom a number of times to verify all the kinematic predictions we made about this material when we subject it to the space environment. So effects of ATOX, radiation and temperature cycling. And we've been on orbit about 22 months now, and it's going well so far. So there's a very simple boom system. We can then make more exotic shapes with the carbon fiber. And here's a great example. So what I have here is what we call a rib, or rib spar. And this is one small part of a much, much larger antenna. You can see a very small antenna here. And you can see the profile, hopefully, on the end of these ribs. We call it a lenticular profile. So when it's deployed, we get all the advantages, once again, of carbon fiber. But if I just pinch this, you'll see the rib collapses, which means we could then roll this rib around a central hub, such that when we release it, it will spring out and give us a radial format of ribs. So this is a very, very lightweight structure that gives us a large deployed diameter on orbit. And we have a saying in the space industry, you can never be too light and your antennas can never be too big. Because the larger the antenna you can deploy on orbit, essentially the higher its commercial value. It's all about what we call link budgets. There's a reason we have these huge satellite dishes trying to listen to very, very distant stars. The other way around, the bigger the dish you have on Earth, the further star away you can listen to. On orbit, the bigger the satellite dish, the higher the quality of your communication link. And with the trend in space engineering to make satellites smaller and smaller and smaller, the laws of physics still prevail. You may make your satellite smaller, but you still need a big antenna to talk to the Earth. So a lot of the value in what we're doing at OSS is about stowage efficiency. What is the largest antenna we can fit in the smallest possible volume? So that's carbon fiber, and that gives us the so-called backing structure. We then need a surface for this antenna. And we're working on two types of surfaces here at OSS. One is a shape memory membrane. So imagine if I got a large steel ball bearing and I poured something like silicon bath sealant over it. And then I remove the ball bearing and turn that surface over. You can imagine a super smooth surface that if I scrunched up and let go, it would naturally want to spring back and take that parabolic shape. That's exactly the principle we take to making large parabolic antenna surfaces. We use a more exotic version, obviously, than bath sealant, and we need that to behave as an RF surface, so we need different types of materials in there. But the principle is exactly the same. If we mold it on a beautiful high precision parabolic, when we get it on orbit and we remove gravity, it will form a precision parabolic. So to allow that structure to get on orbit, we need a backing structure as well. Other types of antenna don't actually need such an exotic membrane. We can get away with this material. So this is, it looks like ladies' tights, but it's not. This is what we call a metal mesh, and I can be really quite brutal with it. I can scrunch it up, but then if I tension it in the appropriate way, I can end up with a super smooth surface. So the wire we're using here has to have a whole range of properties, as you might imagine, to survive in space. When we subject it to temperature extremes, we don't want it to expand and contract too much because it would then distort. So we need a wire with a very good coefficient of thermal expansion, or CTE. We also want the wire to survive an ATOX environment. But most importantly, we need it to behave like a great reflector RF surface. So we end up using a type of metal called gold-plated molybdenum, or gold-plated moly. The molybdenum wire gives us the strength and the thermal properties we want. with a very thin layer of gold on top. That soft metal, that when we tension the underlying molybdenum wire, it causes the gold to bite into itself, because gold's a very soft metal. And that then forms a very, very good electrical surface, because when we're flying through the upper wisps of the atmosphere in low Earth orbit, that can build up a charge and cause a static problem. So gold-plated moly helps dissipate those charges and gives us a lovely electrical surface. This is rather dull and not looking gold, because this isn't gold-plated moly. This is a tungsten wire that we use to carry out all our R&D with. So if we can prove it works with a much cheaper wire such as tungsten, we can then replicate it with gold-plated moly. There's some unusual things about what we're doing here, and most people are surprised that we actually look to the fishing industry to make space antennas. So a very, what might be seen as a low-tech historic industry on Earth is helping the space industry. And the reason we look at the fishing industry is, when you think about fishing nets, they actually have a lot of the same challenges we have with space antenna surfaces. So if you want a fishing net, you want to be able to scrunch it up to put it on the back of a boat, but you want to be able to deploy it and go fishing with it without it tangling. So we need knitting patterns that don't lend themselves to tangling. The other big challenge with a fishing net is, if it gets a hole in it, you don't want rip propagation. You want the hole to be maintained. Well, on orbit, if we have a micrometeorite go through our antenna, the last thing we want to do is have the antenna rip open. So actually what we do is borrow fishing patterns from fishing nets to knit antenna surfaces. But of course, we're not using twine, we're using wires, in this case, that are even thinner than the diameter of a human hair, which causes us a lot of challenges when you're trying to knit in a very precise way at those sorts of dimensions. So there's an example of an antenna surface that, when I apply it to this type of backing structure and we tension it, we get a very, very high stowage efficiency but fantastically performing RF antenna.
Talk to Shefali Sharma, the senior commercial strategist, with regards to investment, promotion, development of next generation design, and construction of disruptive, enabling technology, industry collaborations and opportunities. Shefali demonstrates how skills are transferable between industries, and states it is important to concentrate on data and analytics from space, which is known as downstream, to understand what it means and ultimately its use, as well as how to get this data, which is upstream. Behind the scenes, the Chief Technology Officer, Dr. Juan Reveles, highlighted that typically many of the techniques used in space are coming from civil engineering. The idea of the deployable dome, for example. So it is intriguing to see the process to come back around and start to inform the other way.
So, my name is Shefali Sharma and I am the Senior Commercial Strategist at Oxford Space Systems. My background really is in engineering as well. My bachelor's was in aircraft engineering, and from there on I moved to pursuing a master's in space engineering and astronautics. So I was taken under the wings by a CEO of a mobile company, and he offered me the job, but on the business side of things. So he said, you know, Shefali, you'll be involved in all things business, strategy, investment. But he knew my heart and soul lied with the space industry. So he really gave me that ear to go find a job if possible. If not, then I sort of commit to him and his company sort of full time, which was a very, very privileged position. And while I was there, one of my best friends, I've known her, we did masters together, was working for Oxford Space Systems. So I've been trying to keep an eye on the company, but the website hasn't yet come out at that time. So I called her up, I said, give me the CEO's number, and I called him up right away, and rest is history. So my responsibility really is to help him grow the business and set the company strategy as we move into that commercial exploitation and scaling up phase.
So your background was kind of space engineering, and so did you design kind of spacecraft, or how?
Yes, so as a part of my thesis in bachelor, while I was doing my bachelor, was to design a blended wing body for the aircraft. You might have heard of B-2 bomber.
Yeah.
It's a spacecraft, so I worked on the sort of the body of that. I was quite intrigued by the design, so I just wanted to explore it a bit more. So how we could improve, say, the aerodynamic efficiency of the body. So I worked on that. As a part of my final thesis, I actually worked on a program called a master's thesis called QB50. It's actually a university program, and it was like a university consortium, if you will. Quite a few universities in Europe came together to put this CubeSat in orbit, which was going to look into a few atmospheric parameters that affect the spacecraft in flight. So I worked on the operations side of things on that project. So very, very exciting. But now I've sort of moved away from engineering and now sort of found my feet and ground more on the business side of things. But that said, still an engineer at soul and love working with the engineers, but also how we can, I think what's really exciting about this position I'm working in is, engineers come up with a lot of great ideas, but how can we actually commercialize those ideas and even make money for the business, so to speak, is very, very exciting in itself. Yeah. The technology we are working on is quite disruptive. If you go really do your market research on the sort of technology we're working on, you wouldn't find anything of the sort we are doing at the moment. So it's very much seen as a disruptive, enabling technology for that next generation of satellite services we are talking about, like Internet of Things, machine-to-machine learning, satellite broadband, things like that will all be enabled due to the technology, more so antenna technology we're working on. So very, very exciting times indeed. So actually, you can imagine, as a venture capital backed business, you always have to be sort of inventing new things and looking at ideas which have a lot of growth potential, so to speak. So yes, at the moment, our key focus, which is what our business plan has been based on, is antenna structures like antennas and boom systems. But that said, we are already working on sort of this next generation of even satellites, which we're calling origami sat. So it's a new way of getting the maximum surface out of a satellite when you deploy, say, an antenna in deployable panels, and even solar panels on the other side of the satellite. So it's doing away with that chunky bus in the middle and deploying the whole satellite just as panels and getting the maximum utility out of it, so to speak. So yeah, we've got a patent on that, and we are currently in a customer negotiation, very nascent, but where they love our idea and we're trying to explore it further with them.
How do So I guess that's for me, the origami side is quite interesting. How again, that's what your team has done. You've looked at different industries, if you like, and how do you approach? Did you approach some, professionals in?
Yeah, you've got it exactly. So we don't just do it all in-house. We're very, very collaborative. Well, industry and company more so. So we actually work with the sort of industry leader, so to speak, in origami engineering, and he just happens to be just at our doorstep, Oxford University, and that's a Chinese professor, Dr. Zhong Yu. We work with, and we've worked with him since the beginning of the days, and this was also one of the concepts we worked with him to further mature. So yeah, that's exciting times. Well, how did we come up with the idea? You might have seen in recent news, companies like ISI, Capella Space, they're all coming up with this application called SAR, which is synthetic aperture radar. So it's about imaging Earth from space. So usually you would do that with airborne systems, but we're now trying to enable that sort of service, but through satellites. So you don't have to worry about what the sort of weather is on the day, you don't have to worry about cloud formation, you can just take very clear high resolution pictures of Earth, so to speak. So all these companies are trying to achieve that, and one of the biggest sort of criteria or challenges is having a large surface area for your antenna, so it can take as many pictures as possible and can achieve whatever the mission can achieve. So that's where this idea for Origami Sat came. What if the whole satellite was an antenna on the solar panel? So yeah, that's what we're doing. We are looking sort of horizon scanning, and one of the big aspects of a venture capital backed business is to come up with new ideas and make sure there's always that growth potential, and we're always looking for new ideas.
I wonder, are you already considering maybe doing something, as we spoke with Michael before, something more local to Earth? Are you thinking of coming up with structures? I know you're focused
terrestrial.
On space. Yeah, sure.
Yeah, actually, because that's a very good question, and believe it or not, we get a lot of terrestrial interest, and reason for that is, if you look at the space environment, it's quite harsh from the perspective of, say, temperature extremes or radiation. Similar sort of environment is seen in, say, nuclear or oil and gas industry as well. So our structures will withstand forces, say, or impact, which will be seen by structures operating in that industry. So marine even. So yeah, we get quite a few inquiries. So that is also one of the routes to market but space is our key focus, and we have to deliver that for sure. But as we are growing and scaling up, I don't see why we can't, sort of venture into terrestrial markets, high-tech terrestrial markets, so to speak.
Is there anything that you would consider quite interesting for yourself specifically, or for the, so for me, straight away I'm thinking, okay, emergency shelters, those are the sort of kind of not obvious, but it's like, oh, okay, that makes sense. You can do
exactly
structures that deploy quickly.
Even antennas, the pop-up antennas, which the soldiers in the battlefield, they could just have those pop-up antennas in the backpack, because that's what the concept is about. Very storage efficient, very small and low mass. So you can imagine in the battlefield when they're out and about, you can just have those antennas for comms and things like that. Even the boom systems, we I think had a few inquiries. One of the inquiries was around having our telescopic boom system, and it was like a submarine which will only emerge. They wanted to do the scanning of horizon scanning, whatever ships were on the horizon. They didn't want to make themselves obvious, so it was a sort of defense security type of application. But they wanted to, say, use our boom system that could go up with the antenna, do the scanning, and then come back down. So things like that. I think there's a lot of overlap of technology, and hence that cross-fertilization word we talked of. So yes, we do see a lot of potential for the technology to venture into terrestrial, but it's just that's one of the challenges of a small team when the key focus has to stay with space, and how much of your resources can you actually let go of to invest in those domains is another great challenge to have, I think.
We speak to Michael Loweth, the Business Development Manager, about new space, analysis, scale technology, hardware, infrastructure, telecommunication, and manned space that inspires innovation. Michael expressed, whilst there are space standards and requirements to comply with when developing fit-for-purpose and reliable technologies and systems, it is important to collaborate with other talented professionals. For example, origami specialists, the kite makers, as techniques and methodologies cross-pollinate. It is also important to pay keen attention to the psychological state as well as the physiological, particularly when designing occupational habitats in space.
Thank you. So my name is Michael Loweth, and I work here at Oxford Space Systems in the business development team. So that means that my role is to be forward facing outside of the company, to look at what opportunities exist, to find those people, to talk to them, to explain what we do and how we do it, and then to build those relationships so that we can then work with companies around the world to develop our products and meet their problems and eventually launch things into space. It means that I need to communicate, and I need to have a good understanding of my knowledge and of my products to be able to understand where those niches lie. And I need to work with my two colleagues, Shefali and Mike Lawton, to really understand what are the things that we want to be chasing, where do we go with this technology. So I don't know how much you guys know about Oxford Space Systems, but we started in 2013 and got our real seed funding in 2014. 3 guys, I knew them all, good friends, and they started with some really good ideas, and they've grown the company at a phenomenal rate. Since then, from 3 people, it's nearly doubled in size every year. So now we are 46 people, and more or less. And the whole focus of this growth has been because the things that we are bringing to market, the ideas that we're developing, are really of interest to both our market in space and to so many others around, because they're quite innovative. And it's things like this. So everyone knows carbon fibre, you make racing cars out of it. It's that solid stuff, isn't it, you know? But But what we do is we've looked at the makeup and how we produce this, and we've worked out how we can deploy carbon fibre. So I'll do it in that direction there. So like that. So you can see how we can deploy out what is a very, very light structure. I mean, this version is not so torsionally stiff, but we can develop versions that are. But in particular, in this version, it's very strong in compression. So we can push something out, pull something in, and use this as an actuator or to support lighter components when you really need to. We've managed to get this on orbit. I don't know if you can see the picture in the background, but there's a picture that we got from orbit in November 2016, and that was getting this in orbit, showing that it works. And what was really unique about that was on this small, what they call a CubeSat satellite, we made the longest deployable, in fact retractable structure in space. And what is really unusual for space is we got it from concept to deployment in just 30 months. Now, depending on what industry you work in, 30 months can seem quite a long time. But when you're talking about the space industry, you can't go and fix it if it doesn't work. And that makes the space industry inherently conservative. So though we are cutting edge in a lot of our developments, we're also very conservative, and it's almost Jekyll and Hyde, that we want to make sure it works, especially if it's a critical item. Something like the battery. If the battery dies, your satellite dies. Your deployable structure, if it doesn't deploy out your solar rays, you don't have any power. You can't work anymore. So they're critical items, and therefore people don't want to launch something into space if they don't know it's going to work. Because of that, the average development time to get something into space, you're talking about 5 years if you're lucky, probably 10 years. And so 30 months is a revolutionary change in pace. And it's a great example of what the space industry is calling new space. So like many organisations, like many industries, computer science for example, space is having its own revolution at the moment, where the traditional people who've worked really hard and will spend 5-10 years developing this before they launch into space, we're now getting this revolution that we're actually realising, well, we've done that for 40-50 years. We know how to get into space. Let's start to accept a bit more risk. And it doesn't mean we want to just throw things up and litter space, and you know, we all have hopefully heard that there's issues where there is lots of space debris up there, but we can work around that, and we can design things that accept a bit more risk and can work at a faster pace, and that allows us to really start to be a lot more radical in what we do in space, and to really bring some new ideas. And that's where people are looking at bringing terrestrial capabilities like broadband internet anywhere in the world. You don't just have to plug in or be at home. You can get that anywhere, and so these kind of capabilities are really revolutionising how we think about connectivity, for example. And that's why I'm in the space industry. It's that kind of real exciting, developing new opportunities, and they're not just about making money. A lot of them are an opportunity to really improve our quality of living, improve our understanding of this earth where we live. You know, I don't want to live in a dump. I don't want to live somewhere where you have to step around rubbish all the time, or wear a face mask because the air pollution is so bad. I want to live in a nice planet. And a lot of space is actually about that. It's about looking after our earth. So looking at where the carbon monoxide, carbon dioxide is being produced, where all these greenhouse gases are. There's then things like GPS, helping us get around. There's the telecoms, the most commercial side, but we use that day in, day out. Every day we rely on space for everything we do, least of all our communications. So that's an important part of what we do here. And Oxford Space Systems is really lucky that can tie into a lot of that, because if I show you here, this is a helical antenna, a great example of trying to get some of that data around Earth. But we want to pack this into a small CubeSat satellite. Now, a CubeSat satellite is something that's 10 centimeters by 10 centimeters by 10 centimeters, and that's 1U. We sometimes need bigger satellites, so you'll have a 2U or 3U where you put 2 of these squares together, 2 of these cubes together, or 3 or 6, or build them up like Lego. But 10U is not very big. You've got to really squeeze your engineering to fit that space. And this example of that, so you've got your helical antenna you want, but what we can do here is compress that down so we can fit that into half a U, so half of that space, which then means you've got space underneath it to start to put power, to put your electronics, to do everything else. And then you can deploy this out once you're in space and start to listen out for these signals, so you can start to get information on how your car, how your appliances at home, how different systems are working, and they can just slowly report back to say, hey, I'm getting low on milk, or hey, my tyres are getting low on their tread, we need to start booking this guy in for his garage appointment. And you can start to have machines communicating that low level information so that you're not going to be late for your MOT or something. And that kind of technology we can then scale up. So if I lead over here, I'm not going to deploy this one because this goes 3.5 meters out, but you can see the size of this, again, compresses very low, very small area, but we can send that right out to give you that nice big long antenna to give you the performance you need for that data throughput. And what we're really able to do is to use our understanding of these basic material technologies, build it up using small examples of this is a structure here, this is a material, this is how this works, and slowly get more and more complex, get larger and larger. And by proving something on space like this, you can do that on a very inexpensive satellite. You can then make a much larger version on a much more expensive satellite, and that risk of failure is reduced because you know it works at one level. You can still be quite risky at how quickly you get that out there, but it starts to de-risk, and this is what new space is about. It's understanding the risk that you're willing to accept, knowing you can't just go and fix it, you can't just go and tweak that bit to improve that bit of performance, but what we can do is show that it works, get it up there, get it operating, see how we can best use that technology, and then improve it from there. We're not trying to design a Formula 1 car now. We start with your Mini, your Micra, and build up to your racing car. And that's very much, if I don't know how well that'll come up, but at the entrance we got one of these large helical antennas, and we recently got a press release out where we've been awarded some money from the UK government to develop that antenna, and that's 3, 4, 5 meter diameter. They're large structures, but they deploy using the understanding we gained from this material, and then we launched, and we continue to do our PhD level understanding to get the maths, the understanding of how the chemistry comes together, of how this operates and how strong and rigid it will be in space. But that understanding, building that up, it's bite-sized, it's baby steps, and it's one of the most important things I think the space industry can reaffirm to a lot of other industries, that on these large complex projects, and we'll know these from HS2 and these large projects, they're exactly the same. You've got to break them down into small bite-sized issues, and the more you can empower those teams to deal with different challenges on accuracy of track lines or of whatever the challenge is. That's where your engineers want to be. They want those challenges and finding out solutions. The more you can empower those small teams, the more they can come up with wild, fantastic ideas that when you actually look into it, work out really well. And that's what we try to do here. You know, be as innovative as we can, be as creative, bring in new ideas like new material sciences. Carbon fibre is not new to most of us, but space is very conservative about adopting this because they want to know exactly how it will work in space. We turned around and said, well, the best way to find that out is stick it into space. You know, go and try, find out. So we've got to a point where we can put it into space and see how it works, and then use that to justify all of the analysis that we've done. And we've done a lot of analysis. But hopefully that gives you a little bit of an idea of what we do and why we do it, and why we're so creative and people are interested in what we're doing. At the end of last year, December, we got awarded, we've had a number of awards for our innovation, but one of the awards we got at the end in December was we were ranked 52 out of the top 100 fastest growing companies in the UK, which we're really proud about. But it's more important than that, because space, we've already said, it's 10-year development, it's not fast growing. And of space, the hardware side is the hardest to get into space, because if that fails, you're probably not going to be operating a satellite at the end of it. So we're the slowest part of space, and for us, as the slowest part of a slow industry, to be that fastest growing company in the UK, number 52, that's amazing. That is truly revolutionary, and that shows how we're not only dragging vast parts of the space industry into this new century, we're helping to really invigorate the UK and should hopefully bring some of these ideas to others as well.
It's certainly caught momentum now.
Yeah.
And in terms of, you call it new space, and is there something that we should be aware of, as architects, as any other designer out there who is trying to apply the wisdom from the space industry to kind of other industries on the planet? Is there something that's direct that you...
Yeah, I guess for me, one of the areas I think least about in space, I mean, it's a wide range. There's space art, there's space architecture, there's a whole plethora of different elements of the space industry. But most of what we tend to do, particularly in the UK, is working on satellites, which is where we get information about the health of the Earth, about GPS data, so we know where we are. Telecommunications, we lead the world in telecommunications, and that's fundamental in this day and age, to be connected to not only the person down the road but around the world. Whenever you get the Olympics live from Beijing or wherever else, you're using that satellite infrastructure to provide you that information. So there's an awful lot of business in that, and some real good money and potential for growth in there, and a lot of new space opportunities there. But the area that tends to capture the public interest most is manned space. Now, manned space is the most expensive element, which is why back in the 80s, Maggie Thatcher and those guys, they all decided that they would focus on things like telecoms, and therefore we really had a big bang for our buck and a big return on investment for our buck. So we've really been very commercial in our development. But what we realised recently with people like Tim Peake coming to the fray is that manned space is the area that inspires people, and it's manned space that can have some real societal benefits. It's the easiest opportunity to show and to bring to your children, to say, why should I study maths or physics or chemistry? it's boring. It's exciting, it's invigorating. You've got this great universe out there, look at it, you can get your telescope and have a look. And if you do well enough, you can be one of those astronauts that go out and explore. And even from a religious perspective, the amount of early astronauts that got to space and either found religion or reaffirmed their religious beliefs, that unity of humankind. Why are we fighting over that border? There are no borders from space. And how thin the atmosphere is, how we need to look after this planet we're living on. You know, the Gaia Earth, the green movement, it pretty much began or was embellished and grew because of the space industry, and how the astronauts just happened to take a photo of the Earth as they were going around the moon and then coming back. No one in that industry thought that the most used photo that they ever take, that is, I think, the most used photo in the world, is that marble of an Earth in the distance. That's our planet, that's where we live. We probably should look after it. And it's that kind of inspiration and perspective that space is uniquely empowered to bring to us. You know, you could say going and looking at the Earth's oceans, that's shown us about how we're throwing away all this plastic, how you know, it's a similar kind of aspect. But what space and that manned space opportunity really brings to us is that opportunity to understand how the human body operates in this zero-G environment. It's the best way for us to understand how osteoporosis affects our bones, how you get this bone wastage, this muscle wastage in zero-G, because there's no G forcing your bones to stay strong. And that's a problem that affects a vast majority of women as they get older, and men as well, but it's one of those ones that's very unfair and focuses on the you know, old women and as they're going through menopause. And this is one of the best ways to understand that process and to work out how we can reverse that. Another example that I'm really passionate about myself is that manned space. We're already looking at how we're going to take people so we can not just visit the moon or Mars, but live there. And we're going to have to start being really smart. We're going to create structures that can survive against that harsh radiation environment. So we're going to have to use what they call in situ resource utilization. And that's where we're going to have to work out how do we use that local dirt, that local materials, and make our own mud huts, basically. But yeah, we've done that in the past. We've been very self-sufficient in the past, but we're not now. And we're still very wasteful now. And if you want to understand how we can actually recycle that much more, how we can be that much kinder to our own planet, it's bizarre, but sending people to Mars and giving them that challenge, you're going to have to reuse all of that water. You're going to have to be self-sufficient on a village scale. Well, you're going to get a lot more inspired, intelligent, focused engineers, scientists, people solving that problem, and you can then use those lessons right back home in your house. But you're not going to be able to get those people to work in that at home because they won't be inspired, they won't be driven, they won't be challenged. And that's where the benefit of space is so misunderstood. Why do I want to go and look at another planet? We can't look after this one. It's the other way around. By going and looking at Venus, where you get this massive greenhouse runaway effect for ages, go look at what's happened there. That will give us the cheat book. That will give us what will happen if we don't look after ourselves. It will be in our face, and it will teach us a lot more than we can learn from this planet alone. So I think it is the most expensive area, and we don't do much of it. But really, we should be doing more, because that's where we're going to have to work out how do we build these structures how do we build them so people don't go mad? You know, if you're disconnected from Earth, you're going to feel very alone. How do you manage that psychology? We've really had to do a lot of psychological analysis to understand how to make that space station in space, the ISS, somewhere that can be a home for those astronauts for a year. Jeez, going somewhere else, that's even more of a challenge. And those lessons are what we can use here. What colour should our walls be? How do we make an environment that's more creative or more conducive to harmony? These are things that really can be taken to so many other industries, in architecture particularly. There's a world of challenges for you in the space industry and a world of lessons for you to learn from what we've already done. And we have done a lot of it, or looked a lot into it, but it won't be known to be correct until we actually get there.
The idea is to make the design of the built environment and the architecture accessible to everyone around the world. I talk to space industry professionals on record and share it with you. This research forms a part of the investigation into how safe occupation is designed in response to extreme environments in space. To capture the discoveries and to raise awareness of others, I present to you this research film. Speaking to the source is invaluable, and exploring the frontier of innovation inspires and informs imaginative ideas when we design a constructive built environment. That's it for now. Thank you for your time. I'll see you next chapter.